Okay, so we last talked about what science is. And I mentioned a few things about what science isn't. We don't prove things with science. We actually try to disprove them. Because everybody likes to think they know what's going on, and so you want to prove what you think is actually going on, but we're more prone to actually deceive ourselves, especially if we come up with what we think is a good idea about what's actually going on, than actually finding out what's really going on. So if you come up with a great idea, like I said last time, it was, they're talking about, if I drop my keys, we come up with a hypothesis, right? Why do the keys fall to the ground? Some people actually said gravity. Can you believe that? When I told them that I believe it was actually metalheads in the center of the planet, right? And so metalheads, even though we're talking about magnetism here, not gravity, there's four forces. There's the strong force, the weak force, gravity, and electromagnetism. And if electromagnetism and magnetic fields were actually responsible for gravity, that's metal. Those are mostly iron. That's good. But what's a prediction about everything else? What would happen to everything else that wasn't metal? Float up. We'd all be floating up, right? So, just from this observation alone, now we make a prediction. I just made a prediction, or you made a prediction, that everybody would float up if in fact it was electromagnetism. But we didn't. So we showed that, well, there might still be metalheads down there, we don't know, but that's not what's causing the force of gravity. Okay? So we've refuted that. We've actually showed that, well, that can't be the cause of gravity and while we're all sitting here. So we made a prediction and we actually tested it just by looking around. No one is floating up in the air. If someone started to, I would say cool. You know, that'd be pretty cool, but we're not. I'm sorry, it's too bad. Okay, so science is not a bunch of facts. You can learn a lot of things about the world around you, but there's nothing that actually is proven. There's probabilities on things that make it almost like it's a fact, okay? But nothing is actually ever proven in science. It's all about probabilities. When they say prove it to me, well, that doesn't mean anything. Now, there's no certainty in science. That means you can actually be wrong. That means when new information comes along, you can actually change things. You know how in politics everybody is saying, well, what about flip-flop? You believe in this, then you say you believe in that, you believe in this, you believe in that. So they want consistency, right? Well, the thing is, what happens if something comes along that says your whole worldview was screwy in the first place? Do you hold on to it or not? Kind of like, let's say you don't believe in the theory of gravity, which is actually Einstein's general theory of relativity. I say, okay, go ahead. Why don't you walk up to the top floor and jump off the building and see what happens? You can test it right away, right? So, if new things come along, everything that we know, or we think we know, is provisional. It doesn't mean that it's ever going to change. The original theory of gravity by Newton lasted for, let's see, 1660 to now. So 50, 60 years. It lasted until 1905. Okay, and then Einstein came along. Actually, he came up with special relativity, and then later on he came up with general relativity. And he showed that Newtonian physics and explanation of gravity works pretty well, but it doesn't work entirely well. We'll get to that a little bit more later. Okay. Okay. Whatever you want. It's rotating, and that works maybe we're center of whatever all this is. Now, that's what it looks like. If you were to believe that, without knowing anything, believe what most people believe, or most of you in fact, you didn't say it into the sun and water same as it ever was. 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 And the thing is that now there was a couple of problems with this thing. And they don't follow the same trajectory as the rest of the stars and galaxies out there.
Time isn't holding us. Time isn't after us. Time isn't holding us.
So that doesn't help fit into what our idea of what the universe is. Eventually, someone came up with an idea. Now, I'll say this to you. The Islamic Center for the World back in the 15th century had gotten close, but not quite there. And then someone in Copernicus, Poland, actually came up with this idea that the Earth actually is part of the solar system. Some of the moon and the sun and all that. And it was pretty controversial. Eventually, we came to realize that, in fact, that was actually the case. Okay? So science, for the longest time, it was provisionally accepted by almost everybody that we were at the center of the universe. Now, just because everybody believed that didn't make it so. So, reality is not democratic. It's not changeable. There is something called objective reality. Okay? And when you actually find out things about that reality, and you find that you were wrong, you can actually change those ideas. And that's why science is a very, very powerful way of figuring out what's going on with the universe. So, why do we do science? Any ideas? Why do we do science? Anybody? Yeah? Huh? Say it loud, I'm done.
To make sense of the world.
To make sense of the world. Okay, good. Any other reasons? Yeah?
To find like a real definite like explanation for everything.
Okay. Anything else? So kind of pragmatic. The more we find out about the world, the better it might be, right? Okay. So that's true. There are now, basically, we do science just to figure out what the hell is going on around us. And it's not what we think is going on or what we hope is going on. It's us actually trying to figure out what is really kind of going on, even though, like I mentioned, nothing is ever certain in science. Okay? And then, of course, practical reasons. Science and technology are useful. Now, there's other things that we do in learning about the world. Philosophy, humanities, communication. We do all sorts of different things to learn about the world. Some of those other ways of looking at things, you can actually apply the scientific method. Because what is science? It's actually the scientific method. Okay? And the scientific method, just so you remember, is, well, we'll get to that in 1 second. There's a slide coming up. So, what's the scientific method? Okay. I'm going to do the short version. This is a guy by the name of Richard Feynman, Nobel Prize winning physicist at Caltech, Caltech is in Pasadena. Very bright guy. There's lots of stories about him. Not just he was crazy actually. He loved bongo drums. He did all sorts of stuff. He's dead now, unfortunately. Died of stomach cancer quite a while ago. And then there's a longer one that you guys can actually access at this YouTube. 9 minutes. It goes a little longer into what science actually is. But I'll just play the short version right now. Oh, shoot. So Feynman was a Nobel laureate in physics at Caltech. Unfortunately, He's dead now. Died of cancer. Is a fairly young fellow. He had a lot of different interests, and he basically explains exactly what science is. And so instead of confirming what we believe or what might be true, we actually try to refute it. And the process is simple. We either because of observation or because of theory, we come up with an explanation, and then we have to test the predictions that hypothesis predicts. So, for example, when I dropped the keys earlier, and I said, well, here's my hypothesis. There are metal-headed people in the center of the Earth, and they're the ones that actually cause gravity, and that gravity is associated with electromagnetism and a magnetic field. And so that's why we have gravity. Now, from that hypothesis, the prediction is, well, if it's electromagnetism, the only thing that should then fall to the ground are metal objects, namely things made of iron, and everything else should float away. If we look around, what do we see? We see all the students sitting here. They're not floating around. So we can actually disprove that hypothesis. In other words, that hypothesis is wrong. Hypotheses, like I mentioned, are a dime a dozen. It doesn't matter if you come up with a crazy-ass hypothesis. As long as you can make concrete, specific predictions that are testable, you can prove, or you can actually show that a hypothesis is wrong. And that's the main thing that is so great about science. You can be wrong. That's why it's kind of self-correcting. Okay, so here's the scientific method. Usually start with observation. That means you see something and you wonder what's causing it. Okay? So you end up with a question. What the hell is causing that? You come up with what's called a hypothesis, right? Hypothesis is nothing more hold on a second. Okay. Nothing more than an explanation. As I mentioned, the hypothesis explanations are a dime a dozen. You can come up with any kind of explanation you want. When Feynman said you could guess, you can. No one's going to shoot you for coming up with a bad explanation. The fact that I dropped the keys and I said, oh, there's metal heads, and that's an explanation, right? Wasn't an adequate explanation, but it's an explanation nonetheless. Explanations generally make predictions. The prediction was that it was actually electromagnetism that causes gravity. And if that's the case, the prediction is the only thing that should actually fall to the ground were metal objects made of iron, things like that, right? Well, that wasn't the case. So right there we refuted. Now we can toss that explanation out, experiment or observation, we reach a conclusion, right? If it's wrong, you'll see we'll come back around and propose another hypothesis. You can keep doing that as long as you want. Okay. So this is a real simple explanation. The car won't start. Why won't it start? You think, oh, it's a dead battery. If the hypothesis is correct, this prediction, then the car will start if you replace the battery. You open up the hood of the car and you find out that there is no battery. You've refuted the hypothesis that there's that there isn't a battery. In fact, there's not even an engine. So, right, you have to start over. What happened to my engine? You know, someone left it. But if the battery is replaced and the car doesn't start, then that's not the hypothesis. If the car does start, for now, that's a good idea that it's actually the battery. Now, there might be something that's causing the battery not to actually charge. So you might find out later that your battery keeps going dead. Then you have to come up with another explanation further down the line about ultimate causes. Okay, so as I mentioned, hypotheses usually come from observations that generate questions. You want to figure out what the hell is going on. Now, that's not necessarily always the case. Sometimes it comes from theory, from just thinking about things. Forget about observation. In fact, Einstein was so radical because he actually thought if he was at the head of a beam of light, what would it look like? They knew at that time that there was a speed limit of the universe. Still the case. You can actually make light go slower by passing through things, but in general, light travels at a certain speed. It doesn't change. Okay? Now, at the same time, people thought that time was also constant. And in fact, Einstein, because of his ideas in terms of theory and seeing things, realized that it wasn't, that time isn't constant, that it changes. If you're on, let's say, a hillside and you see a train passing by and dual bolts of lightning strike at the same time, from your vantage point, those lightning bolts struck at the same time. If you were in the train, it would be different. Because you are actually moving along this track towards one bolt and away from another, if you actually measured things correctly, from the inside, you would find out that, in fact, they didn't happen at the same time. Really strange, weird stuff. Okay. So, we do hypothesis generating and testing, in fact, all the time. We decide what we're going to wear today. I see a lot of people, including myself, who are wearing shorts. Anybody in here wearing a heavy overcoat? No. Why? Yeah. You can actually, from observation, and so when you wake up in the morning and say, oh, it's too hot to wear an overcoat, I think I'll wear this. You're basing that on an observation. You're generating a hypothesis. And right there you know right away that you shouldn't wear an overcoat. Now, I've seen people in the dead of winter wearing really light clothes for whatever reason. So there's other reasons to wear clothes besides just the weather. Another thing is, what's the best route to take to school? Let's say you're driving to school from Pasadena or something. If it was 4 in the morning, what do you think would be the best way? Freeway or surface streets? Freeway. Okay. Rush hour. Who knows, right? How would you actually tell? Well, it turns out that, okay, you think, now there's another thing. A lot of times you go the same way because of what you learned initially. So it's kind of like legacy. You find it all the time in things we do. We believe things a certain way. We keep doing them over and over again, even though they may not be, let's say, the best way, fastest way. Now, if you were going to actually test which is the best route to take, what would you do in terms of testing it? Anybody? Huh?
Get a timer and just drive.
Yeah?
Yeah.
Okay. And what about different, would you do it at the same time every day or different times or what?
Keep it constant, so do it at 5 a.m. this day and 5 a.m. the next day.
Okay. Okay. So now, would you just use one car or would you use many? With many different drivers? Anybody? It turns out you want a representative sample of all the drivers that are out there. Now, obviously, if you have some little pokey Kia or something like that, and someone else has a Lamborghini, the Kia might get there faster because the guy in the Lamborghini is pulled over and gets a ticket for trying to go 200 miles an hour when it's back-to-back traffic. Okay, but you can set up an experiment to actually test, which is the best way to do it. So we do this kind of thing all the time in our lives. Of course, we also have what are called beliefs. And like I said, you might have gone a certain way and you keep doing it over and over again, whether you know it's faster or not. And that's a belief. And beliefs are they're kind of a shorthand in dealing with reality. You think they're right, but they're not necessarily. It'd be kind of stupid to go around everything you see and you have to set up an experiment to figure out what the hell's going on. Okay? So we have a shorthand, it's called beliefs. Unfortunately, a lot of those beliefs they're unsupported sometimes, and they can be misleading. Okay. So, here's a question. Should we look for evidence to confirm it?
No.
Why?
Confirmation bias.
Confirmation bias. Exactly. Should we look for evidence to refute it? Anybody? Well, let's say I come up with a really great hypothesis, but I really want to know if it's true or not. Now, what you really want to do is you want to try to blow it up. If you can find a prediction from the hypothesis and test it, and actually test it rigorously, try to blow it up, and it's still standing, it means there's a little bit of provisional support for that hypothesis. Doesn't mean it's correct. Just means, well, you've come up with a test, and it seems there's some evidence to support it. You keep trying to come up with new ideas to test over and over and over again, and you fail to blow it up. I'm talking about really you take nuclear weapons and try to blow the hell out of it, right? It's still standing like, what is it, rabbit, the battery, still stand, whatever it is, right? Okay. So, what does it mean to be falsifiable? Anybody? What? To be proven wrong. Exactly. That's the secret to science. Can you come up with a test, a rigorous test, that tests these predictions that you can actually show they're wrong? Okay. So here's this thing again: observation, question, hypothesis, prediction, test, experiment, or additional observation. Test supports the hypothesis because it supports the prediction. You made a prediction, you test it somehow, and it's consistent with that hypothesis then. Or the experiment, it doesn't support, the prediction fails. Okay? Then you come back around, and where do you go? You end up going back to another explanation that you try to test. Now, there have been scientists that have gone down the wrong rabbit hole their whole careers. It can be a bitter pill to swallow when you think what you thought was right and all the evidence suggested, and then you find out later that your whole career has gone up in smoke. But not really, because you actually learned something. Of course, tell that to the granting agencies. Okay. So, now, what's a theory? No, okay. Okay, a scientific theory is different than it's only a theory. And you can read what this says. There we go. Anybody, what's a theory? Anybody, is it different than a hypothesis?
It's basically a hypothesis that you've tested and found nothing wrong with.
Okay, so it becomes, it looks like it's actually real. Okay, now theories aren't, now when someone says like with the theory of evolution by natural selection, you've probably heard people say, oh, it's only a theory. Is that, what kind of theory is that? Huh? What do you think that kind of theory? When someone says, oh, it's only a theory, when you hear that, what does that sound like to you?
That is just one of multiple possibilities.
It's kind of like an opinion. Oh, it's only a theory.
And they're trying to dismiss it.
You just kind of dismiss it. You say, oh, it's only a theory, right? Like the germ theory of disease. It's only a theory. Vaccines cause autism, so don't take vaccines, even though they predict. See, vaccines, it's only a theory. Don't worry about getting vaccines. Okay. Now, that's what's called a conjecture. We'll just say it's an opinion. It's different than a scientific theory. A scientific theory actually not only may it come from, let's say, one hypothesis, it may include many hypotheses for an overall framework for kind of explaining some natural phenomenon in the world. Like theory of gravity. Einstein's theory of general relativity, it makes a bunch of different predictions. In fact, one was just recently, the last holdout to general relativity was discovered that it was actually consistent with that. They found gravity waves. You probably might have heard about that with this big detector, two detectors that were kilometers long. Oh, by the way, I'm starting a company. If any of you guys have problems, you have a bad back, you have lupus, you have cancer, come to me because I'm starting up a new company called Gravitational Wave Therapeutics. Brand new. It works incredibly well. I'm going to start having things on TV. People can I'll give you free coupons, in fact, to come and get fixed. I promise you I'll cure your cancer. I'll cure your love life. Because gravitational waves are passing through us and from us all the time. And we can actually use them to make life better. So Gravitational Wave Therapeutics is my new company. We can talk about it afterwards. Okay? But anyway, a scientific theory is okay, so here's our scientific method again. And as I mentioned, we come up with observation, question, a model or hypothesis. A lot of people say model, it doesn't matter. And it's comprised of a set of assumptions that should reveal predictions that follow logically from the assumptions. And then you do empirical tests of it. in some context, the model can be put, or the hypothesis can be put in a more general context, like Darwin's theory of evolution by natural selection, or general evolutionary theory now. It's much bigger than when he was thinking about it. And then the model's refined over time, if it's independently validated. But if it fails one prediction and fails fundamentally, then you have to, no matter how beautiful the theory is, it's wrong. Okay? Now, sometimes a theory is only partially wrong. So, a good example is Newton's theory of gravity. We still use Newton's theory of gravity when sending out spacecraft to Mars and the Moon and circulating around the Earth and all that. His equations using calculus are still as good as ever, and you'll get to the right place at about the right time. It just turns out that Einstein came up with it helped modify, essentially, it took Newtonian gravitation and added some things that better explained what was actually going on. So, a theory, you can just toss a theory if it's completely wrong, or if it seems somewhat right, you might find that you can actually modify it. So, here's a question: is science robust to an incorrect hypothesis or theory? Well, it kind of is, yeah. Even if people believe something, making false assumptions, eventually you'll find out. Someone might come up with and question it, trying to make a name for herself or himself, or just because they think they're wrong. So there's always people out there that are going to try to refute your hypothesis, which is good. It doesn't mean it's personal. Oh, you're stupid for coming with, no. It says, I think your hypothesis might be incorrect for these reasons, and this is how you test it. Okay? So the nice thing is that if you're wrong, it doesn't mean you're going to be wrong forever. So in the ants count video that you see, or that you saw, I want you to know, first of all, that all the ants in an ant colony like that, they're all females. There's a few males around, as I mentioned, but they're really only sperm delivery devices. So the thing is, with an ant colony like that, there's actually only one breeding female, that's the queen. All the others are female workers, but they can be at different sizes. Some are soldiers, some are workers that care for the eggs, some are foragers, all these kinds of different things. There's only, like I said, a few males. The males are actually what's called haploid. We'll learn a little bit about that. So a normal individual is diploid, where they get a chromosome from their mother and a chromosome from their father. In these ants, the males are haploid. They only get the chromosome from their mother, which is the queen. And then the female ants, because they don't have any of their own offspring, they don't actually, they're diploid, but they're more related to each other than they would be normally between brothers and sisters. They're actually 75% related, but you don't have to know that. So this is kind of how you go about a hypothesis like that. As you can see, there was the hypothesis about ants, perhaps ants count to find their way around. And then you make predictions and about what would happen, let's say, if the ants had longer legs or shorter legs, all that kind of stuff. And in this case, the data support the hypothesis. It doesn't mean that the hypothesis is absolutely true. It means now that there's what's called provisional support. Okay. A lot of people are terrified of science and mathematics. Who hates math in here? Okay, that's good. 2 plus 2 is a little too strong for you, huh? Okay. And science. Oh, it seems so difficult. But as I kind of explained to you, it's really simple. Now, you have to think about consequences and all that, and coming up with explanations, and how to test them. But beyond that, you kind of use it all the time in your life. And it's a good way to kind of test some of your own assumptions, if you can think about it a little bit more. So, an example of how we use it all the time, right? Now, so here we are again. My computer won't start because, so, what constitutes a scientific hypothesis or theory? Usually based on observations or theory, like Einstein's. You couldn't actually observe what it felt like to be at the head of a beam of light. Proposes an explanation. It must be testable. That means you can refute it. You can show it's incorrect. It makes specific, unambiguous predictions. So you have to be careful when you come up with a hypothesis. If it's too general, you can make predictions and you test them and it always comes up right, but you're really not testing anything. Okay? Okay, so, and if you can't test it, then it's not actually a scientific hypothesis. Now, what constitutes a good experiment? Okay, so these are the kinds of experiments you guys are probably familiar with. Lab experiments. They don't all have to be in labs, by the way. As I mentioned, you could do the car thing. It's not in a lab. You can even use different cars. You could also take off at different times. And then you're actually testing a number of different hypotheses about how long it takes from one place to another. You might figure out that, well, it might depend on the car you're driving. It might be the driver. It also might be the time of day, right? Then there's another thing that's going on. You try to minimize bias, like confirmation bias, whether it's with the experimenter or with the subjects that are being experimented on. And then we use something called statistics. Probably heard things about statistics that make you like, well, they're not real. They are, and they're useful. And you can actually test the predictions statistically. Now, in a really perfect world, you're testing one variable, everything else is held constant. I'll finish this up, stop here, but just wait. You create two groups that are similar, but randomly assigning subjects to each group, then randomly choose which group will get the treatment. So that means, let's say it's vitamin C and cold. And then the control group, who doesn't get the treatment. And then you kind of match up the participants, so about the same age, sex, all that, you take that into account. The more things you can control for, the better designed your experiment. We'll end there. So, anybody going anywhere this weekend? Huh? It's Labor Day weekend. Anything? Huh? San Francisco. Anybody else? Paris? No, okay. Have a good time. Yeah. It's not for biology.
I'm a biochemistry major. Should I be in a different bio?
You might. Go talk to an advisor in the chemistry department. I haven't. You can also look at at the course, the big thing that tells you.
But I don't know if
Oh, then you want to get out of here.
Yeah.
Yeah.
Okay.
Because otherwise, you want to take the class that'll actually count towards your major, right? Right? Okay. This won't. This will eat up a GE. And GEs are actually really important because they can even out your schedule so you're not taking death trap classes all the time. So you want to drop this,
Okay.
and you want to try to get into a 106 or 107 class. Doesn't matter.
Okay.
But you're going to have to take. You're going to want to have to take both.
So I don't have to take a bio before 106?
No, these are entry-level bios for majors.
Okay, then thank you.
Sure.
So the email of the class, it tells you
Oh, I forgot to do that. Yeah. Okay.
I haven't been looking like this. Is it because I'm trying to crash
Oh yeah.
both?
Which ones?
I don't need the lab, I just need the...
Right. Forget about the lab. So this here. So you're on the waiting list, right?
Number 1.
Okay, that's right. We're just going to have to wait and see if people drop out. When they do, you'll automatically move up, and you'll be number 1. You'll be enrolled in the class. Okay?
So, I emailed you about the class and I'm coming back to about one of the maintenance because I'm taking it.
Right. So we're going to have to wait. Yeah. Okay. That's all. I can't give you a permission number because I haven't heard anything. They might open up the number of people we can accept. If that happens, then I'll give you a permission number. I don't know if you get in the class or not.
But how many people are on the waiting list?
I think there's 6 or 7, something like that.
But they come first and me?
They automatically go in, yeah, if they're on the waiting list. Since you can't because you've already taken the class and you didn't pass it.
But do I have any chance?
There's always a chance, like I said, a lot of times we haven't heard anything, we will soon, about whether opening up extra students.
You don't know when you...
It'll probably be next week sometime.
Okay, then I'll just come.
Yeah, so I wouldn't fret too much,
Okay.
okay? Hi,
I just need to know because I'm an exam student.
yeah,
And I can't find that. I'm not registered for the bio. I
uh-huh.
was registered on the physics class, but I don't like it.
What's that?
I was registered for a physics class.
Uh-huh.
I don't like it and I would like to go to the bio.
Okay, what's your major?
Biochemistry.
Oh, you don't want to take this class.
It's just for science because I need 15 units for science.
Oh, okay.
And that's just-
It would be better if you took something like Bio 106, which you're going to need, or Bio 107 if you can get into one of those classes.
Okay.
Okay? Otherwise, I mean, if you, first of all, are you on the waiting list or not? Yeah. The chance then of getting into this class is pretty small. You're going to have to try to crash. But I would try to crash something. You could always crash, pick another GE that you'll need that actually can't be used for anything else, just for the GE that you need. But you don't want to take this class because you won't get any credit for it, really. Okay?
Thank you.
Hi, how's it going, man? I emailed you. My name is Michael, by the way.
Uh-huh.
Yeah, I was on the, I was on waitlist. I'm on number 4, but I just want to know, so I'm trying to get my GE social science. So would this just, would this count, right?
Yeah, so what's your major?
CTBA.
What?
CTBA.
What's that?
Like cinema, television. arts.
Oh, that,
I'm just trying to,
this would be a GE for you.
Yeah,
You need one science GE.
Yeah, so I'm trying to
Yeah.
So I know, I heard you were talking to them, so I know I pretty much just wait for the end of the week and then see how
Well,
that
probably
goes.
next week will go much better.
Yeah, I mean, that's a lot of open spots. And maybe
Yeah, I know.
So maybe if all goes well, I feel like.
Yeah. I mean, don't freak out yet.
Oh no.
Okay.
I still want to
Yeah.
be in this class. So even if even if they won't let me, I would definitely try to go next semester.
Okay.
But
Okay.
I definitely want to for sure try to get it done.
Okay, good. Okay, well, let's see, what's your name again? Michael?
Yeah, but you
Okay.
can call me Andre. That's my other name.
Okay,
Yeah.
you can call me Mo.
Mo. Okay.
Or as long as you don't call me asshole, it's fine.
You know.
Okay. Yeah, so,
Yeah.
okay, great.
I'll keep all. This is the last class, so not until next week. So if
Yeah.
anything, I'll email you and check.
Yeah, I'll be out of town until next Monday.
Okay, so.
So, Yeah.
If I don't get a response, then
But don't worry, I still have email and all that, so you can still email me.
Alright, thanks so much.
Okay? Good luck.
Alright, thanks.
Oh yeah, one more thing. Okay, so can I just email you, just like so to know how many kids you're able to take in? That way I will be able to know, and I will just like, you know.
Yeah, email me.
Email you, okay.
And I'll put your name on my list,
Okay.
and then we'll keep up and see what
Okay.
happens.
Okay, so then.
What's your name?
Stephanie Reyes.
Okay.
Yeah.
Oh, yeah, I know.
Yeah,
Okay, you're on the list then.
Yeah, okay. So I just email you like around next week? Will
Yeah.
that be fine, like
Yeah.
on Monday?
Yeah, Monday or Tuesday,
Okay,
something
and
like
then
that.
to see what happens.
Yeah.
Okay, then thank you so much.
Okay, thanks.